So very good morning one and all. We are learning the subject of electromagnetics. Today we will learn the chapter of the waveguide and the numerical on the waveguide. We will see today the type of the waveguide on which we are going to simplify the numerical, that is of a circular waveguide as well as the rectangular waveguide. Theoretical part related to waveguide already we have studied. Now come towards the numerical, rectangular as well as circular waveguides. Start with the numerical one. Take a numerical number one. Find the cutoff frequency for TE12 mode TE12 mode in a hollow rectangular waveguides whose dimensions are listed below. That is A part. A is equals to 2.286 centimeter, comma B is equals to 1.016 centimeter. Similarly, B part, A is equals to 1.016 centimeter, comma B is equals to 2.286 centimeter. C part is your A is equals to 1 centimeter, B is a 1 centimeter, and D part is A is equals to 10 centimeter and B is a 10 centimeter. Likewise, the dimensions are given, and that is hollow rectangular waveguide is here, and we need to calculate the cutoff frequency in which mode, that is nothing but the 1-2 mode, that is a MN mode, the EMN mode. So how we can continue, how we can simplify this numerical which is on the rectangular waveguide. At the beginning you need to note on that is a rectangular waveguide. Next line, the cutoff frequency for TE12 mode is given by rectangular waveguide. Next line, the cutoff frequency for TE12 mode is given by FC is equals to, yesterday also we have seen in one of the lecture how to calculate the cutoff frequency. So this is the formula in the rectangular waveguide to calculate the cutoff frequency related to the velocity of propagation and all. So FC is equals to V0 by 2 root of M by A plus N by B. M and N are also the mode of what we can say, the transmission or the transfers. Okay, 0 1 1 0 1 1 1 2 0 2 likewise, and the A and the B are nothing but the rectangular dimensions. So every in each section, that is A part, B part, C part, D part, just substitute the value of A and the B in this formula of the cutoff frequency, you will get the answer. So what is my first step in the A part? That is A is a 2.286 centimeter and B is 1.016 centimeter. Substitute this here. Okay, so which mode is here? 1 2 or directly mentioned, that is a transverse electric mode. Okay, and that to 1 2 mode. So here M is equals to, note down here also at one side, M is equals to 1, that is mandatory to write this value. M is equals to 1 and N is equals to 2, then only it is possible to substitute here 1 and the 2. Then later on substitute the value of the A and the B. So likewise you can calculate. So what is what we can say, um, anything is mentioned apart from that in the numerical? Nothing. Okay, so you can continue here. So velocity of light, you can take 3 into 10 to the power 8. So that you need to convert into, it's a centimeter dimensions are mentioned. That's why we have converted. So that's why 3 into 10 to the power 10 is there, divided by 2 root of 1 and 2 are nothing but the MN values, and the A and the B are nothing but 2.286 and 1.016 of a bracket whole square. So in this way you will get, just cross verify all of you with your calculator whether you are getting this 30.215 gigahertz or not. 30.215 gigahertz. Now, while you are going to substitute the value of A and the B again, the mode will be the same one, that is M is equals to 1 and N is equals to 2. And you are going to substitute here. So definitely 1.016 centimeter and 2.286 centimeter. We have kept in the centimeter only. So this will be the same one. Okay, we are not converting this centimeter into the meter. So later on, after substituting this one, squaring and the root and then multiplication with this one, you will get as 19.75 gigahertz. Third part, that is nothing but A is equals to 1 centimeter, B is equals to 1 centimeter. Substitute this value. Okay, so here will be your the 1 by 1 in case will be there. Here will be the 2 by 1. So here will be the 1 and here will be the 2. So 1 square, 2 square, root of that. Okay, and so in this way you will get as 33.54 gigahertz. Now the last study part, that is A is at 10 centimeter, B is at again the 10 centimeter. So 1 by 10 and 2 by 10 will be the case. So 1 by 10 of bracket of square plus 2 by 10 of bracket of square. Okay, we just squaring these two and root, take the root and then multiply with this one. You will get 3.354 gigahertz. 3.354 gigahertz. So in this way you
Not
can
getting.
simplify the numerical. Yes.
Not getting answer on that.
34.39 gigahertz A part. 34 point, let me take 34.8. Have you converted Shashank? Apart from you, anyone is getting?
Ma'am, it is 33 into 10 to the power 8 now.
What I have just now tell you, here is the centimeter cases, na? So we have to take here. We need to consider that also part. Centimeter. Actually, we want into the meter. So that part we need to keep in the mind. That's why we are not taking 8 here. That will mean the 10 to the power so and so. At the beginning only I have told you. So no, go for the numerical number 2. So that numerical number 2 is nothing but a rectangular waveguide with the dimensions. A rectangular waveguide with the dimensions 3 into 2 centimeter, 3 into 2 centimeter, 3 into 2 centimeter, operates at 10 gigahertz, operate at 10 gigahertz, operates at 10 gigahertz. First off, find cutoff frequency, find cutoff frequency, that is FC, cutoff frequency is FC, comma lambda c, FC, comma lambda c, lambda g, beta g, only lambda, and the VP of TE10 mode, of TE10 mode, of TE10 mode. So what is mentioned here? Same rectangular waveguide is here with the dimension is mentioned. Two dimensions are mentioned along with your the frequency. The dimensions are nothing but 3 and 2 centimeter. Keep in your mind that is in the centimeter. Okay, and the frequency is given, that is a 10 gigahertz. You need to calculate the cutoff. You need to calculate the wavelength. Okay, that too in the what we can say the group wavelength as well as your the cutoff frequency and the group phase constant. Beta g is nothing but the group phase constant, and Vp is nothing but the velocity of propagation. And which mode is mentioned here? That is nothing but TE10 mode is mentioned here. So you just note down at the beginning, you just mention which waveguide you are going to use, the heading of that waveguide, then the parameter which is given in the numerical. All of you start with that.
Ma'am,
So you will, yes. So you will get as A
if
is
we are taking
equals,
lambda is equal to,
if if A is equals to 3 centimeter, B is equals to 2 centimeter, and the F frequency is equals to 10 gigahertz. 10 gigahertz. So that is nothing but 10 raised to the power. How will be here? The mega is nothing but the 6, giga is nothing but the 9. So what you need to take here? you need to take here, that is a 3 into 10 raised to the power, instead of taking here the 9, what we are taking, because this is the 2 centimeter, again this one is also the 2 centimeter, okay, 2 into 8, so 2 will be as it is, okay. What is my a is nothing but a into b, so a is nothing but the 3 and b is nothing but the 2, so 3 and the 2, so any one we need to take, that is nothing but my a, so 2 into a, that is nothing but the 3 here, okay. So this thing into the 10 raised to the power, that you need to concentrate on that, which part, that is nothing but you are the what centimeter case, so this centimeter into 10 raised to the power will be go up, okay, so that will be in the plus, so it will be your the, instead of 8 here will be the 10, so you will get as a cutoff frequency is nothing but the 0.5 into 10 raised to the power 10, okay. And if you want to convert into the standard form, that is either in the mega or the giga, so you will get as a 5 gigahertz. Similarly, the lambda c is nothing but the critical, or you can say the cutoff wavelength. This is the cutoff frequency and this is the cutoff wavelength, okay. So lambda c is equals to 2a directly, again so 2 into 3, that is in the centimeter directly we have taken here. So in this is the normal wavelength, and this is the critical or the cutoff wavelength, and already we are aware from the resonance part what is mean by the what you can say the cutoff or the critical case, and what is mean by the normal, okay. Already we have discussed on that. So this lambda is equals to, how we are getting this one, that is a velocity of propagation that we are taking, and the normal frequency, that is nothing but 10, given in the numerical, that is nothing but 10 gigahertz. So 3 into 10 raised to power is this one, and this 10 into 10 raised to power 9. So in this way you will get again in the centimeter. Now come towards the next, that is nothing but your the group wavelength. Group wavelength can be determined
And why
as
this is not in
lambda.
meter?
Hello.
If we are taking 10 to the power 10, na,
Hello.
we are taking standard value, no,
What
for
we are
lambda,
taking?
lambda,
Huh,
10 to the power 3 into 10 to the power 10, na,
huh,
for a meter.
huh. Getting.
And why it is a 3 centimeter, not in meter?
You can convert this one. Anyhow, you can convert this one. If you are taking this centimeter, this will be different. If you are taking in the meter, this will be different. You can convert. If this lambda c, if you are taking in the centimeter, here should be in the centimeter. Both, if you are taking in the centimeter, you need to take care. If you're not taking in the centimeter, then you need to take this again you need to convert this centimeter into the meter, again this you need to convert into the meter, like this. So the lambda g is nothing but the group wavelength. So this group wavelength can be determined as a normal wavelength divided by your what we can say the root of, either you may take the root or you can say directly by the 1 by 2. So root of 1 minus in bracket lambda by lambda c of whole square root of 1 by 2. Either take 1 by 2 or directly take the root. Now here the substitute the value of the lambda and substitute the value of the lambda c. So lambda c again the cutoff or the critical wavelength, and the lambda is the normal, okay. So in this way you can substitute and you can find that a group wavelength, okay. How we are saying the group multiple wavelengths, if you are coming, if you are considering the length is a larger one, that time you need to think about the group wavelength. The second part is nothing but you are the, again if you are going to substitute that value of your the what we can say the lambdas and other parameters, so you will get as the group wavelength is nothing but 3.464 centimeter, okay. So if you don't want to convert into the centimeter, just cross verify yourself if is there any much more difference is there or not, okay. So that is also possible. If you are going to substitute the one is in the meter, the entire term should be in the meter only. If you are taking in the centimeter, entire starting from the beginning to the end, that should be in the meter itself. Okay. So in this way, just substitute the value of here the 3, then 6, and the other value in the root also. Then you will get as 3.464 in the centimeter. At the from the beginning, if we are taking the in the centimeter. Now the phase constant is nothing but denoted by the beta and the 2 group. So 2 pi by lambda will be the formula. Already we have done in the uniform plane wave also how we can calculate the beta. Beta is equals to 2 pi by lambda. But here if I am interested in the group, so definitely that will be 2 pi by lambda g. So here if you are going to substitute this value, you will get as 1.813, that is radian per centimeter. And velocity of propagation is nothing but you are the omega by beta, again the omega you can take as a 2 pi f. You can substitute the value of the f, you can substitute the value of the beta 1.813, and the f you can take as a 10 gigahertz. So in this way you can get his 34.64 into 10 to the power what we can say 8, that is meter per second. Find the broad wall dimension of rectangular waveguide. Find the broad wall dimension of rectangular waveguide when the cutoff frequency for when the cutoff frequency for TE10 mode is TE10 mode is A part is 3 gigahertz, B part is 30 gigahertz. A part is 3 gigahertz and B part is 30 gigahertz. Full stop. So this numerical is also related to the rectangular waveguide, and what they are asking here, find the broad wall dimensions. That is nothing but simply they are asking about the dimensions, but not here the A and the B. They are asking about only the A. Why A? Just a broad mention here. The A will be treated as a broad wall. Okay, because A and the B are the two dimensions in the rectangular. But here we are interested just specifically they are mentioning the broad the word. That's why. Secondly, when the cutoff frequency for TEM mode is the given the two cutoff frequency, that is the 3 gigahertz as well as the 30 gigahertz. If we are going to substitute this value and if we are in the TE10 mode at that time, how we can calculate that dimension? So indirectly they given here in this case. Indirectly they given in the previous cases we have the dimensions were there and we need to calculate the cutoff and the wavelength, but in this case they given the cutoff what you can say the critical frequency or the cutoff frequency, and we need to calculate the dimensions. So how we can what we can say solve this numerical? Before just going to start, I will just mention here which waveguide is there. So rectangular waveguide heading should be rectangular waveguide, and in the A part what is given, FC is given, that is nothing but the cutoff frequency is given 3 gigahertz, for which mode, that is nothing but TE10 mode. So this FC is equals to, that is a V0 by 2A. V0 by 2A. So what is that? A is nothing but the broad wall dimensions. Okay, A is nothing but broad wall dimensions. So what is my A? A is equals to, if I am going to take my A outside, then the V0 by 2 into FC will be here. So you can take as a 3 gigahertz, and this will be the 3 into 10 raised to the power 10. Okay, so in this way you will calculate as A is equals to 0.5 into 10. 0.5 into 10. How we got 10? You just do simplify this one, you will get. Okay, so finally if you want to convert into the centimeter, definitely you will get as a 5 centimeter. 5 centimeter. What is the change in the A and the B? Simply the cutoff frequency is changing. Instead of 3 gigahertz, the cutoff frequency is of a 30 gigahertz. Instead of 3 gigahertz, 30 gigahertz is the cutoff frequency, and the mode is the same one. You can substitute on the change in the, instead of 3, here will be the 30 giga. You can substitute that one, and that is in the centimeter. Okay, directly that is in the centimeter, no issue for that. The next is nothing but a hollow rectangular waveguide operates. A hollow rectangular waveguides operates at a f is equals to 1 gigahertz. F is equals to 1 gigahertz, and it has the dimension of, it has the dimension of 5 into 2 centimeter, 5 into 2 centimeter. Check whether TE21 mode, check whether TE21 mode propagates or not. Check whether TE21 mode propagates or not. Propagates or not. So wave propagation we need to find out here. So while you are going to finding the wave propagation, we know very well the propagation what we can say propagation constant or gamma is equals to lambda alpha plus j beta. Already we have done in the transmission line, and the uniform plane wave was the basic formula related to the gamma. But in this case, in the wavelength, somewhat different formula is related to that gamma. That is nothing but the propagation constant. Okay, because we need to take care about the dimension, we need to take care about the modes. So mode will be there, the dimension will be there, and as per that only we need to substitute the value. Okay, so what is that? The propagation constant which is denoted in the, what we can say, t, either the te or the ta mode, is nothing but the gamma g. Okay, and this gamma g, this we are taking in the real part, we are not taking at present in the imaginary part, because other values are not mentioned. So directly you can start and you can solve also, but later on if nothing is mentioned, at that time you can substitute the j will be the zero term if nothing is mentioned, but at present, at beginning, you can start with the real term. Okay, so this gamma g is equals to root of, we are talking about the rectangular b, remember. Okay, that is important because the formula will be changed for the circular also. So this gamma g will be equals to root of, in bracket, m pi by a whole square plus n pi by b whole square. Here the pi is additional value is given here, along with your the omega square, mu and the epsilon. This is the derived expression. Okay, while we are learning the theoretical subject, that time only these parameters will come, and uh, accordingly we can conclude that the expression, final expression for the any value can be get with the help of that only. So here the propagation constant gamma is equals to root of m, and the n are nothing but the modes, a and the b are nothing but the rectangular dimensions. The substitute omega is the angular frequency, mu and epsilons are nothing but permittivity and the permeability. Substitute the value which is given. So how we what is given here in the, if you observe in the numerical, you will be able to find a and the b part, that is in the centimeter. You may convert into the meter, because if you want this in the meter, so that time you can convert 5 centimeter into the meter, 2 centimeter into the meter, and the frequency is the 1 gigahertz, that is a 10 to the power 9 hertz, and the mode is nothing but te to 1. So where the m is equals to 2 and n is equals to 1. We know very well the constant value mu 0 and epsilon 0 are nothing but the 4 pi 10 to the power minus 7, 8.854, 10 to the power minus 12. Already we have simplified many numerical on this one, where the constant values were this one only, the helium per meter and the, what we can say, the farad per meter. So this gamma group of gamma, yeah, propagation of constant gamma g for the te1 mode, if you are going to substitute this value here also, that is 2 pi f. So instead of 2 pi f, this omega square is there, so 4 pi square. Okay, and f square. So likewise you can substitute the value, you will get as 200.1. Nothing is given em, this part is a real part. Okay, but if you want into the imaginary, why we want in the imaginary? Because the propagation constant gamma is nothing but alpha plus j beta. So if indirectly, if we are going to add and finding, so the propagation constant we are getting, no doubt at all, the one value that is nothing but the 200, that is a np plus meter, nipper per meter, no doubt. But in that case also we should know what is my attenuation constant, or what is my the, what you can say, the phase constant. So here the attenuation constant, as nothing is there in the imaginary part, that is a j0, j0 nothing is there. So indirectly you can say alpha plus j beta. So beta will be the 0, that is the phase constant is a 0, and the attenuation constant both. Okay, after converting, so in short you can say the propagation constant is equals to attenuation constant, but the phase constant will be the 0. A copper rectangular cavity resonator, a copper rectangular cavity resonator is structured by 3 by 3 is to 1 is to 4, 3 into 1 into 4 centimeter. A copper rectangular cavity resonator is structured by 3 into 1 into 4 centimeter. Find its resonant frequency for, find its resonant frequency for TM110 mode, TM110 mode, TM110 mode. Stop. So what is given here? The rectangular cavity resonant is there. Okay, uh, rectangular shape type of a resonator is there, and that is of a three dimension, A, B, and the C. Three dimensions are there. Find its resonant frequency. find its resonant frequency, that is nothing but the FR. Okay, if we are having a resonator, okay, and that too in the rectangular shape, at that time if mode is given and we need to calculate at that time, that is nothing but the resonant frequency. Okay, so this resonant frequency again, either you may uh, just because of this, see here the modes 110, okay, 110, how we are taking here, the concentration is on, you can say, what you can say here, the mode is nothing but M, N, and other last mode is nothing but the C part mode, that is M and N. And one yesterday in one of the slide I have shown you the X and P. Likewise, if the distance is increasing at that time, then the N as well as the P will be increasing. Okay, similar to that only here the dimensions are increasing, that is nothing but the A, B, and the C dimensions. Okay, so at that time what we need to take care, simply here there is no as such role of mode, but we should remember which mode is there at for the specially cavity resonator, and that to rectangular. So here we are interested in the resonance frequency. So velocity of light you can take, or the velocity of propagation you can take here, that is a v by 2, and the root of 1 by a square plus 1 by b square plus 1 by c square. So all these, see here how they are converted directly. So A, B, and the C. A is nothing but the 3 centimeter, which is converted into the meter, 0.03 meter. 1 centimeter, again 0.01 meter. 4 centimeter, 0.04 meter. So this centimeter is converted into the meter. That's why directly they are taken as here the 3 into 10 to the power 8 by 2. Here will be the root of this 0.03, 0.01, and 0.04, all are in the meters and the squaring. So if you are doing and converting, so you will be able to find here, that is nothing but directly you will be able to find, that is the resonant frequency will be equals to, after in the root term, then the multiplying with the 3 into 10 to the power 8 divided by 2, all these things you will be able to find as 1.625, that is 10 to the power 10. If you want to convert into the standard form, you will be get as 16.25 gigahertz. 16.25 gigahertz is nothing but your the resonant frequency. A copper walled rectangular cavity resonator is structured by 3 is to 1 is to 4 centimeter, 3 is to 1 is to 4 centimeter, and operates at a dominant modes of a TE and TM, dominant modes of a TE and the TM, whose to find its resonant frequency and quality factor. Find its resonant frequency and quality factor. First, the conductivity of the copper is 5.8 into 10 raised to the power 7 mho per meter. The conductivity of a copper is 5.8 into 10 raised to the power 7 mho per meter. First, there is a air inside the cavity. There is a air inside the cavity. There is a air inside the cavity. So here the TEA mode is mentioned. Okay, why we are saying it's a dominant mode? The effect of here the either the M and the N, what will be that case, and depending upon that, because 110, 100 are the dominant modes. Additional apart from that, MN is nothing but the dominant modes. And if we are interested to find out in the resonant frequency in that particular dominant, so at that time we will be able to find as, so that FR is equals to V by 2 root of 1 by A square plus 1 by B square. 1 by A square plus 1 by B square. Now how we can find again this the V that is mentioned here, but no need to calculate every time this V, because already we are having the value already we can, and already we can substitute. After substituting these two only, directly we are getting this one 3 into 10 to the power. No need to do every time this case, that is a 3 into 10 to the power 8 meter per second every time. So A dimension is mentioned here, the 3 centimeter converted to the meter, B is the 1 centimeter converted to the meter. Now FR will be the V by 2, so you can substitute root of 1 by A and 1 by B, you can substitute this value of a whole square bracket. So you just, this part will be the 4 times 1 and here will be the 10,000. Likewise, these two will be add and root of that will be multiplied with the this 3 into 10 to the power 8 by 2. So you will get 1.5 into 10 to the power 8 into the root term is this one only. So in this way you can convert into the standard, that is nothing but 15.8 gigahertz. Now come to the point for the TE mode, resonant frequency of a dominant, that is nothing but again here the if the changes are going on, that is nothing but the dominancy is coming instead of 100, here is mentioned the 101 is there at that time. What will be the change here? What will be the change here? If you observe in the previous case, what was that? Here was the again the 4 centimeter. If dominant third part we never check. Here only 1 by A and 1 by B we have taken. But if you are going to concentrate on the third part also, that time also possible. This 4 centimeter will be converted to the meter instead of taking the first and the third. So first and second in the first case, that is 100, 101 in that case first and the third case. So here the L, that is nothing but the C part you can take. Okay, only change in the meter of your third dimension, that is nothing but the C part you can say, that is the 4 centimeter. This 4 centimeter is converted into this meter 0.04. Okay, and you can substitute that value. So you will get as resonant frequency 6.24 gigahertz. 6.24 gigahertz. Now the question arises here. What is the question? Find out the quality factor, and we know very well the quality factor can be denoted as the Q, and that to which